Okay. Here's our combined SSOC graph, and ours is not linear by any means anywhere. We have several different regions. Region 1 is the lower range, and it's to about 50% input, and it stays really close to 0 output. And then region 2 starts increasing drastically with a big anyways, sorry. Slope, thank you, that's the word. Region 3, still increasing, big slope. And then region 4 is a little bit less of a slope. Unique qualities of our system, decreasing intervals are different than increasing intervals, and I probably need to point that out, that the blue line is our decreasing, and then you can see our increasing does a little bit differently. And it kind of looks like multimedia up here, so maybe that explains it. And like I said, SSOC is not linear. Here's our gain results. They vary throughout all the different voltage ranges. This one's really interesting. It's really big compared to the decreasing. It's the biggest difference within all the gains. And here's our dead time results. We have a really small dead time, so the differences really aren't as big as they would look because it's really just 0.05 of the difference. But they vary as well all throughout the ranges. And the time constant. Again, the 15 to 30 volt range has a really big increasing tau. So here is a step response graph, step up from 70 to 77. You can see our output is the red line, the input is the blue, and it looks like step up 7%. Here is the model. Green is the input. You can't see the experimental input because they line up perfectly. And then our model output and experimental output. Model output is orange, experimental is red. And here is a step down. It looks a lot like the other one. Color code's the same. It's just going down instead of up. And here are the results for the increasing. It's 15 to 45 volts were large, but they were about the same. And then 0 to 15, the gain right here was really low compared to all the other ones. It's kind of the opposite in this one. The mid-range is lower for dead time, and the outer ranges are significantly higher. And the time constant, the general tau was around 5, but then we had some that were completely different than the other ones. And here is for the step down, same idea. We got low gain for the lower regions and then higher in the 30 to 75 volts. Dead time, 30 to 45 volt range was the one that didn't really follow the norm, but generally the other ones stayed about the same. And like I said, the difference really isn't as big as it looks because our dead time is so small. So for the sine input function, here's our input function, transfer function for it. And here is an example of our sine response experiment. You can see where we will want to calculate the phase shift and the amplitude ratio. This darker blue is the input, and then the lighter blue is the output. Here's some of our results. The sine frequency response is done from the 15 to 30 volt range, 30 to 45, and 60 to 75. And we all got around, our case value varied from 0.15 to 0.25 generally. And here are our results for tau. Again, our tau seems to vary a lot through our voltage system, through our ranges. and a 30 to 45 was the experimental was very different from the model. The FU for sine frequency response, we have around 5 hertz for 15 to 30 volts, 3 for 30 to 45, and 8 from 60 to 75. So these are all different, like always. And these follow a nice upwards pattern for our KCQ, but 15 to 30 volts was a lot smaller than the higher regions. Here is a Bodie plot, and this was from the 15 to 30 volt range, and you can see how we calculated all our numbers, K, FU, KCU order. And here is a combination. And our data, when we were doing our models to fit the experimental, we would try to match up the points that right before it curves, like it starts curving down. So that's what we're looking at right around here. And then after that, they all start varying. Down here, we were looking to fit the model and experimental at around 180 degrees. And so this, we had trouble with this 30 to 45 volts getting to 180 degrees for some reason. So that's why we just had to make our best guess and fit it like that. Here's for our relay response. Our set point, blue is input and red is the output. And here shows how some of the things we use to calculate our numbers. T2, T1, and then the delta C and 75% of delta C. Here's the results for the relay KCU. 0 to 15 volt had a pretty big one. I think it was 38 compared to 45 to 60 volt range because it was only around 2 all the way. And then the FUs are opposite from that. 0 to 15 volts had smaller, and the 45 to 60 volts was a lot larger. So here are the parameters that we came up with that we chose that were the best for our system. And we're not sure about this tau or this T0, why they're so much bigger. So we'll probably need to go back and look at them again and run an experiment or two again. Same thing for this gain. We're not really sure why it's so big, but that's what our models told us to use. Here's the feedback control loop, getting into the root locus theory. Here's our transfer functions, KC, which is GC of S, and then this one that we've been using, G of S. And using Paday's approximation, that's what we're going to use to get the open loop transfer function, which is then multiplied together. And we use the roots of finding the roots of the denominator of the open loop transfer function, and where zeta is the damping ratio. And there's different effects of the damping ratio. If it's equal to 1, then it's considered critically damped, but it's monotonic and stable, just like when it's overdamped, which is a zeta greater than 1. And then if you would like underdamped, you're going to look for from 0 to 1 zeta. And then if it's equal to 0, it's undamped with sustained oscillation. Negative 1 to 0 is unstable and it will grow in oscillation. And then less than negative 1 is runaway, which is monotonic and unstable. Here is the root locus modeling. Right here where your line crosses the imaginary axis is where you get your ultimate value of Kc. And then back here is the overdamped region, and where your numbers turn from imaginary to real is the critical damping, and then right through here is underdamped region. Decay is associated with overshoot percentages, so this is what you'll use. These are some of the normal values or the common values you offer your customer when you're looking for different overshoot. With a damping ratio of 1, you're going to have critical decay with no overshoot. Damping ratio of 0.707 is 1/500th decay with 50% overshoot. Damping ratio of 0.344 is 1/10 decay with 30% overshoot. 0.215 is the quarter decay with 4% overshoot, and then no damping ratio gives you 1 decay with 100% overshoot. Here is one of the root locus plots, and this was for the 15 to 30 volt range, and you use your trig. So your quarter decay is at the 78 degree angle, and then the 1/10 is 70, 1/500 is 45, and then you have your critical damping and your ultimate. Here's a comparison of all the different voltage ranges and the KC values we found. Notice up here, these all were off scale because the 0 to 15 volt range has such a small K value, so it made the KC values very big compared to the other ones. So I just did it this way so you can see the difference in all the other ones. And they go in decreasing fashion for most of them except the critical damping. This was just to kind of simplify the previous slide, just to show you where our smallest and largest values came from. And so you can see that all our largest Ks came from 0 to 15 volts, and all the smallest ones came from the 60 to 75 volts, except for this one, of course, which was 30 to 45 volts. This is a comparison of the response in root locus FU values, and these noted right here were the ones that were relayed. The ones not noted are the Bodie. And so the relay from 45 to 60 volts, it was a big variance, as well as in the 60 to 75 volts. But these weren't as bad. And again, we had this number is off scale, the root is off scale. And so the lower voltage ranges had a lot more variance than the higher voltage ranges. Using the final value theorem, we got C of T values for the specified KCs. And so the relay ones gave numbers close to 1, and the other ones just varied between. Some of our conclusions. The upper, mid, and lower ranges do not share the same behavior. Comparing root and response FUs, ranges from 0 to 45 volts had less variance than from 45 to 75 volts. And comparing root and response KCUs, 0 to 30 volt ranges had significantly more deviation than 30 to 75 volt ranges. When we put together this chart so you could just see what values of KC you would choose for different damping situations. But it's important to understand the customer's goals before choosing the KC value. So for use in a range of 0 to 15 volts, if you want over damped, you're going to use a KC from 0 to 15. Critically damped KC needs to equal 15. Under damped, 15 to 186, and then a quarter decay is 38. For 15 to 30 volts, you're going to use a KC from 0 to 0.26 for overdamped. Critical damping, you're going to want it to equal 2.6. 2.6 to 34 is your underdamped region, and your quarter decay will be 7.2. For 30 to 45 volts, you're going to have 0 to 0.2 for overdamped. Critical damping is going to equal 0.2, and then 0.2 to 12 is your underdamped KC value range. For quarter decay, you're going to use 2.6. 45 to 60 volts, 0 to 4.9 is your overdamped region for KC. Critical damping will happen at 4.9. Underdamped will be from 4.9 to 27, and your quarter decay will be 7.7. 60 to 75 volts, you'll have, for overdamped, you're going to do a KC value from 0 to 0.21. Critical damping will be at 0.21. 0.21 to 6 is for underdamping, and your quarter decay will happen at 0.9.